So good evening. Am I audible to you all? Hello. Am I audible?
Yes, ma'am.
Yeah. Okay. So I think nobody else would be joining. So let us start today's session. So good evening, Sarla, and this is the sixth session on fundamentals of electronic materials and devices. So we will be solving a few questions based on week six contents. So I hope that you don't have any doubts or queries regarding the contents of the previous week. So if you have any doubts and queries, either you can post it in the discussion forum or you can mail me at sandra.pmrf@gmail.com. So let us start today's sessions. So in last class, we had seen like basics of PN junctions, different types of junctions that are formed and how carrier concentration based problems work, how depletion width based problems work. So we'll extend that discussion this week as well as we'll be seeing new concepts exclusively related to PN junction. So we'll start with few logical questions and then move on to numericals. So let us start with today's first question. So first question is, choose the correct statement from the following. So basically, first option is PN junction is a two terminal one junction device, and transistor is a three terminal two junction device. So as option B, you have PN junction is two terminal one junction, and transistor is two terminal three junction device. So option C is again PN junction, one terminal two junction device, and transistor two terminal three junction. And your final option, option D, is again PN junction is one terminal two junction device, and transistor is, this is two terminal one junction, two terminal one junction, and transistor is a two terminal three junction device. So which of these options are true? So first option is PN junction is a one terminal. First option is PN junction is a two terminal one junction device and transistor is a three terminal two junction device. Second option, PN junction is a two terminal one junction device and transistor is a two terminal three junction device. Third option is a PN junction is a one terminal two junction and transistor is a three terminal two junction device. And final option is PN junction is a two terminal one junction device and transistor is a two terminal three junction device. So which of this is true? Basically, you need to know how many junctions or terminals are there in a PN junction as well as a transistor. So out of these options, which is true? Or you can just unmute and tell me what is a PN junction and what is a transistor. So based on that, we can select.
PN junction is a two terminal one junction device, madam.
Yeah,
Transistor uh, three terminal two junction
two
device.
junctions. So basically, the answer is option A. PN junction is a two terminal device. PN junction is basically two terminal device, two terminal, one junction device, and transistor is a three terminal, two junction device. And in PN junction, if you see, there are two terminals, one P and one N, and both of them has a junction. And in case of transistor, there is three terminals. Either you can have 3P and 2P and 1N region, or 2N and 1P region. And there are two junctions, two interfaces between the 2P and 1N, which forms the PNP transistor, or the two interfaces between the 2N and 1P, which forms an NPN transistor. So we have two types. PNP transistor is there. Also we have NPN. But nonetheless, it has three terminals like 1, 2, 3 and two junctions at the two interfaces. And PN junction on the other hand has only two terminals, that is one is P, one is N, and a junction between them. Okay. So next question is a bipolar junction transistor, that is a BJT, consists of two PN junctions. So we have the emitter base junction and the base collector junction. The depletion region lies almost entirely in the base. The depletion region lies almost entirely in the base in emitter base junction. But in base collector junction, it is divided between B and C, that is base and collector. Why? That's the question. So basically, the question is that there is a bipolar junction transistor BJT consists of two PN junctions. There is the emitter base junction and the base collector junction. So first in the emitter base junction, that is in EB, what happens is that the depletion region lies entirely in the base. But in case of the base collector junction, the depletion region lies between B and C, that is between the base and collector. So what is the reason for this? So you have to answer with respect to doping. What could be a possible reason for this? So we had learned in last class what happens to the depletion width when we are increasing or decreasing doping. So based on that you can answer. So there is a BJT, it has an emitter base and base collector junctions. In the emitter base, the depletion region lies entirely in the base, while in the base collector junction, it is divided. That is, part will be in the base, part will be in the collector. What is the reason for this? If you want, you can check other sources, your textbooks or notes, or you can refer to any other sources and then find an answer. And the clue is that the depletion width where it lies depends upon the extent of doping in the material. You can take your time and you can use this session to actually use it as a learning session also, so that you need not revise later. So you can check what is a BJT and how the depletion width lies. So have you got the answers? Otherwise, I will tell you why. Like, okay. So basically, they are telling that in a BJT, you have in a BJT, you have the emitter base junction and the collector base collector junction. So it is told that in the emitter base junction, the depletion region lies entirely in the base. And in case of this junction, it lies equally, meaning that half of it is lying in the base region, half of it is lying in the collector region. So the answer is actually option B, which means that so we are comparing these two. We have the emitter, we have the base, and it is told that the depletion region lies in the base. The reason is that the emitter with respect to base region, so basically the emitter is there, right? Emitter and base, if you are comparing, emitter and base, if you are comparing, emitter is heavily doped. So heavily doped. So we have, yeah, sorry for the interruption. So with respect to the base, emitter region is heavily doped, and since the emitter region is heavily doped, the depletion region will lie mostly in the base. So the depletion region will lie mostly in the base. But when we are considering the base and the collector, they are comparably doped, meaning that the doping levels would be somewhat similar. That is the region why the depletion region would be distributed equally in the base and the collector. So the answer is option B. So what happens is that in a bipolar junction transistor, there is the emitter base region and the base collector region, and compared to the base, emitter region is heavily doped, and since the emitter region is heavily doped, depletion region would lie in the base, and comparing the base and collector, they are comparatively doped, and therefore the depletion region will lie equally in both of them. So is it clear?
Yes, ma'am.
Yeah. So we'll go to the next question. Consider an NPN JFET. Which of the following statements is true? Option A, this is a current control device with a P channel between the source and drain. Then option B is the N channel exists in the absence of gate voltage. Then option C, the voltage applied to the gate reduces the width of the P channel. And finally, the voltage applied to the gate increases the width of P channel. So we have an NPN JFET. Which of the following statements is true? So this is a current controlled device with a P channel between the source and drain. The N channel exists in the absence of gate voltage. The voltage applied to the gate reduces the width of the P channel. And finally, the voltage applied to the gate increases the width of the P channel. So we are considering an NPN JFET, and for an NPN JFET, which of the following statements is true? So you can check what is an NPN JFET, and from that you will be able to understand whether it's a current controlled or voltage controlled device, and where the P channel lies, and how the width of the P channel is affected by the voltage applied across the gate. Yeah, you can go through your notes, or like if you have any ideas about NPN JFET, you will be able to answer directly. Yeah, so please take your time, like since it is a friendly discussion, and you can just go through your notes and find out. Like there is no harm in trying to answer. You can think about NPN JFETs, or just check them out. Just read about NPN JFET just right now, and then tell me like whether it's a current controlled or voltage controlled device, and what happens to the channel and their width when a voltage is applied across the gate. So can you please check and let me know? Yeah, it's a voltage controlled device. Yes, so that is true, meaning that the first option is wrong. So it's not the current control device. So next we have, yeah, so that's correct. So basically it's a voltage control device. So the first option is wrong. So it's a voltage control device, and then we have the options. The N channel exists in the absence of gate voltage. The voltage applied to the gate reduces the width of each channel. Voltage applied to the gate increases the width of each channel. So these three things are there. So out of this, which is true? When a voltage is applied to the gate, what happens to the width of each channel? Will it actually have an effect, or will it remain the same, or will this just get pinched off? So in that case, which of these options is true? Option C. Okay, you are telling that the voltage applied to the gate reduces the width of the P channel. And okay, any other option? Is there any other option? So it's not a voltage, it's not a current control device, it's a voltage control device. Okay, that is there. So we have an NPN, which means that it has a P channel. And then therefore the second option, that is the N channel exists in the absence of gate voltage, that's also wrong. Now when a voltage is applied to the gate, what happens to the width of the P channel? It actually reduces. Therefore the option C is correct. Okay. So now we can move to the next question. Now we'll have a numerical problem. Consider a MOS structure using N-type silicon, and its ND value is given as 7 into 10 power 16 centimeter power minus 3. What is the voltage required to make the surface intrinsic? Give your answer in words. And also it is given that Ni is 10 power 10 centimeter power minus 3, and temperature is 300 Kelvin. So option A is 0.41, option B is 0.61, option C is 0.82, and option D is 1.04. So we have a MOS structure. So in that the ND value is given. It is said that it is an N type, therefore they have given the ND. And what is the voltage that is required to make the surface intrinsic? So Ni is given as 10 power 10 and temperature is 300 Kelvin. So basically it's a metal oxide semiconductor structure. So it's a layered structure and it is an N type. So what voltage has to be supplied so that it becomes intrinsic in nature? So you can check and solve and let me know. Yeah, for solving this problem, I'll give you a hint. The thing is that first we have to find the equation for electron concentration at the surface. That is an equation for which connects Ns and Ni. So from there, you have to find the relationship between 5s and 5b. And once you get to know that 5s and 5b is equal, we have an equation for 5b. And using that equation, we can find out 5s because since 5b and 5s are equal. So if you can start working on the equation with Ns, you can start there. Like electron concentration at the surface, Ns can be written as a particular equation. So in that it is, from the question it is told that we have to find out the voltage to make the surface intrinsic. So we have to find the voltage that becomes N is equal to Ni. So what happens? 5s becomes equal to 5b. So then using the equation for 5b, you can find out the value. Yeah, hello, hello, hello. Hello, hello. Can you hear me? Yeah, yeah. So no, I was asking whether class is there today. Then just now master posted na it is on 5th and 7th. That's why I called. Yeah. Okay. So I think okay, but I don't think now it's already 8. Now my work is not done yet. So maybe we can go tomorrow. So anyway, he scheduled it for tomorrow only. You'll come back on Monday, no? Okay. Tuesday is what date? Tuesday is 11th. You'll just miss only 2 classes then. Rest you will be there. Yeah. Okay, okay. Like anyway, I'm not done with work. I like thought of posting in group, even I forgot it. Yeah, okay, chalo, bye bye. हाँ. Yeah, so I see that you haven't answered yet, so let me move on to the answers now. So basically, the electron concentration at the surface of MOS, that is a metal oxide semiconductor, is given by Ns is equal to Ni e power 5s minus 5b divided by kb into T. Okay, surface, so where phi s is the surface potential, phi b is the bulk potential. So here they have asked us to find the voltage at which the surface becomes intrinsic. So surface carrier concentration in the n-type state is actually this thing. But when it becomes intrinsic in state, Nd actually becomes Ni at the surface. Nd becomes Ni at surface. So what happens? Ns equal to Ni you can write. So in that case, this equation become n is equal to ns e power 5s minus 5b by kb into t. So these things will cancel, or we can say that e power 5s minus 5b by kb into t is equal to 1. And when we take ln on both sides, we get 5s minus 5b by kb into t is equal to 0. So in that case, what happens? 5s becomes equal to 5b. 5s becomes equal to 5b. That is, the surface potential becomes equal to bulk potential. So this is the like formula wise way of answering the question. If logically also we can speak, like when ns becomes equal to ni, the potential also becomes the same. So phi is equal to 5b. Now phi b has an equation that EFN bulk minus EFI bulk so phi b is equal to, that is the Fermi level in bulk by Fermi level in intrinsic state in bulk. So this is in the n-type state, this is in the intrinsic state. That is equal to kBT ln nd by ni. So basically 5b we can get as kb into t ln nd by ni. So now can you solve this and let me know? So here we already know that 5s is equal to 5b. So that is the voltage value that we want. So can you solve this and tell me the answer? So using the equation kb into t ln nd by ni, we can find the voltage value at which the surface becomes intrinsic. So what is this value? Kb is the Boltzmann's constant, D is the temperature, and in Ln we have Ni, which is the intrinsic carrier concentration, and we have Nd, which is the doped carrier concentration. So what were the values? Yeah, T was 300, Ni is equal to 10 power 10 per centimeter cube, and Nd is 7 into 10 power 16 per centimeter cube. So using this, can you substitute and let me know? So what is the answer on substitution? ഒരു മൂന്നാല് ക്വസ്റ്റ്യൻ കൂടെ ചെയ്ത് അവസാനിപ്പിക്കണം. ആകെ ഒരാളേ ഉള്ളൂ. ആകെ ഒരാളേ ഉള്ളൂ. ആ കുട്ടിയാണെങ്കിൽ മിണ്ടുന്നു. ഇത് ഒന്നേ വാങ്ങാം, അല്ലേ വെക്കാം. എന്ത് വേണം? ഏത് വേണം? പോസ്റ്റ് വേഗം പറയട്ടെ, ചെന്നിട്ടൊക്കെ പറയും. വെക്കണോ വാങ്ങണോ? വെക്കണോ വാങ്ങണോ? ക്ഷീണം ഉണ്ടോ? മെയ് നാളത്തേക്കല്ലേ? ചേച്ചി തീർത്ത് പെണ്ണ പെണ്ണ മിണ്ടുന്നില്ല. പക്ഷെ എല്ലാരും ഉണ്ടെങ്കിൽ നല്ല രസമാണ്. പക്ഷെ ഇതാരും മിണ്ടുന്നില്ല. പോകുക ചേച്ചി പറയട്ടെ. പോടാ എടാ പോടാ. മനസ്സല്ലേ വരില്ലേ? തന്ന എനിക്ക് എന്താ ഒന്ന് പോവോ സ്പീഡി? നീ എനിക്ക് NPTEL ലാഭം തല്ലു വാങ്ങി തരൂ. So the answer is option C, 0.41 volts. Yeah, that is because we have 5B is equal to, so for that, okay, 5B is equal to 1.38 into 10 power minus 23 into 300 ln 10 power 10 by 7 into 10 power 16. So since it is a ratio, we need not change the units, and therefore we get 0.41 volts. So this is the voltage that is required such that the surface behaves intrinsically. So as a continuity, this question, next question is continuation using same parameters. What is the voltage required to create strong inversion at the surface? Leaving everything else same, like same intrinsic carrier concentration, same level of ND, same temperature, same material. So initially we saw what is the number of carrier, like what is the voltage required to make it intrinsic. Now what is the voltage required to make the surface strongly inverted? Yeah, so you can check for the equation for strong inversion. And there is a slight change in the relation between the bulk potential and surface potential. So if you know the relation, you can just modify the equation and find the answer. So what is the voltage required to create strong inversion at the same surface? Kalia, take you. Yeah, so basically you have to think what happens to the surface potential when there is strong inversion in with respect to the bulk potential at engine C. Carrier concentration, what happens? 5s it becomes equal to 5 right? But same thing, what happens to the surface potential because of strong inversion, you have to find out. And just if you modify the same equation, K, T, B, Ln, N, Nd by Ni, you will get the value for strong inversion. Yeah. So basically what happens is that at strong inversion, only one small change happens. 5s becomes equal to 2 times 5b. So now can you tell me what is the voltage required for creating strong inversion? 5s actually becomes 2 times 5. Option C. Is the option C your okay? Let's see. Yeah, here is yeah, that's option C. Is 0.82 volts. So next we'll see. Next question is choose the correct option with respect P channel MOSFET. So option A is it has an N type source, N type drain, and P type bulb. Option B is P type source, N-type drain, and P-type bulb. Option C is P-type source again, P-type drain, and N-type bulb. Finally, option D is N-type source, P-type drain, and N-type bulb. So for P-channel MOSFET, what is the configuration? It's a P-channel MOSFET. You have to tell me what is the source, what is the drain, and what is the bulb. You can check for what are P-channel MOSFETs, and directly you can see how the configuration works for a P-channel MOSFET. What is the source, drain, and bulb. So basically a P-channel MOSFET has a P-type source, a P-type drain, and an N-type bulb. So here we are talking about a P-channel MOSFET, and here we have a P-type source, P-type drain, and an N-type bulb. So the next question is, why is titanium preferred over silica for MOSFET technology? This is a logical question. You can just maybe, even if you Google it, you will get basic concept of how, on which aspect of the semiconductor material it depends. Basically, why is TiO2 preferred over silica for MOSFET technology? It has something to do with tunneling of carriers across the outside layer and the property of material that prevents it. So how would TiO2 and SiO2 differ in tunneling of carriers across the oxide layer. Which property is responsible for this tunneling, or which property prevents the tunneling of carriers across the oxide layer? That is the reason why titania is preferred over silica in MOSFET technology. What property is that? You can make some random guesses also, that's also fine. Hello, am I audible?
Yes, ma'am.
Yeah. So the answer is that the relative permittivity of TiO2 is higher than that of SiO2, and this prevents the tunneling. This prevents tunneling of carriers across the oxide layer. So that is why TiO2 is preferred over silica in MOSFET technology. So next question is, in an N-type gallium arsenide metal oxide semiconductor at 300 Kelvin, donor concentration is 2 into 10 power 16 per meter cube, sorry, centimeter cube, and Ni is 2 into 10 power 6 per centimeter cube. Calculate the hole and electron concentration at the surface during inversion, during strong inversion. Your answer should be in centimeter per minus 3. So basically there is an N-type gallium arsenide metal oxide semiconductor of 300 Kelvin. Donor concentration of Na is given as 2 into 10 power 16 per centimeter cube, and Ni or intrinsic carrier concentration is 2 into 10 power 6 per centimeter cube. We have to find the hole and electron concentration at the surface during strong inversion. So Nd is given to you, Ni is given to you. You can calculate 5p, 5s, and from 5e and 5s, you have to find the value of ns and ps. That is basically you have to find ns and ps. During strong inversion, what is the hole and electron concentration at the surface? This is the electron concentration at surface, this is the hole concentration at surface, and you have to find it during strong inversion. That is when 5s is equal to 2 times of 5. In this condition, what is the value of ns and n? Here s denotes the surface concentration. Eh? Eh? Yeah. So in this question, basically what you have to do is ND is given to you as 2 into 10 power 16 per centimeter cube. So it basically becomes 2 into 10 to the power 22 per meter cube. And Ni is given to you as 2 into 10 power 6 per centimeter cube, which becomes 2 into 10 power 12 per meter cube. And all of this happens at temperature is equal to 300 Kelvin. Right. First we have to find phi b. So that will be your Kb into T ln Nd by Ni. So on substituting, what we will get 1.38 into 10 power minus 23 into 300 into ln 2 into 10 power 22 by 2 into 10 power 12. So this becomes equal to approximately 9.53 into 10 power minus 20. This is in joules. Since we are substituting this in this Boltzmann's constant here, it will be in joules. We have to convert it into electron volt. It becomes approximately equal to 0.6 electron volt. Now 5s is 2 times 5e. That is there. You can find that. Now what you have to find is you have to find out PS and NS. Next is you have to find out PS and NS. That is the main aim of your question. You have to find out PS and NS. Basically, PS is equal to Ni exponential of 5s minus 5b divided by kT. Okay, so it becomes Ni, that is 2 into 10 power 12 exponential of 5s minus 5b. You have to substitute these both at 1.38 into 10 power minus 23 into 300. So this electron volt value is actually not needed. You can directly substitute it in this thing as well. So 5s and 5b you take and substitute, and you get approximately equal to 2 into 10 power 16 per centimeter cube. And finally, once you know the value of PS, you can find out NS by the basic equation. We have Ni square is equal to NS into PS. Therefore, Ni square divided by PS. Ni square value is already given to you, 2 into 10 power 12. The whole square divided by 2 into 10 power is equal to 2 into 10 power 22 per meter cube. 2 into 10 power 22. So basically, you have 2 into 10 power minus 4 per centimeter. So your NS value is 2 into 10 power minus 4 per centimeter cube, and your PS value is 2 into 10 power 16 per centimeter cube. So these are the two values. So actually what you do is first you have to find out the value 5b. Then your 5s is 2 times of 5b. You take it in the initial thing itself. Yeah, so this is actually, yeah. And here you have to find PS and 5s. Your PS equation is Ni exponential 5s minus 5b into kT. We know 5s and 5b. With that we find the value of PS. Once you know PS, you can directly use the equation for NS as Ni square divided by PS. And you will get the final answers to be 2 into 10 power minus 4 and 2 into 10 power 16. So is that clear?
Yes, ma'am.
Yeah. Okay. So with that, we'll move on to the final question. Question is, consider P-type silicon based metal oxide semiconductor at 300 Kelvin. Acceptor concentration here 2 into 10 power 16 per centimeter cube. And I is again given as 10 power 10 per centimeter cube. And dielectric constant is 11.9 for silicon. What is the total depletion width at strong inversion? So we have a p-type semiconductor that is silicon based, which is a metal oxide semiconductor at 300 Kelvin. Accepted concentration is given 2 into 10 power 16. Intrinsic carrier concentration is given. Dielectric constant is also given. What is the total depletion width at strong inversion? You have a direct equation for the depletion width at strong inversion, and in that, if you directly substitute the value that is given to you, you will directly get the. Look, how you derive for the depletion width is yet another process that is not required here. If you can just remember what is the depletion width equation at strong inversion, directly it can be substituted. Else you will have to first derive the equation for width using 5V and then use in this case. So that is not required. It's a direct equation, and this equation is actually similar to the one we use for finding depletion width in PN junctions, that the ones we have seen in last class. So basically the equation for depletion with that strong inversion is given as Wm is equal to 2 times root of epsilon 0 epsilon r q t ln Na by Ni divided by E square Na. So you have almost everything given to you. So basically you just substitute the whole thing. Epsilon 0 epsilon r. What we do here is that the dielectric constant is given to you. So we multiply it with permittivity of free speed 8.85 into 10 power minus 12 into dielectric constant of silicon. So this is 9. Then into K value 1.38 into 10 power minus 23 into temperature 300 into Ln. Both of that you can either convert it into meter or you can use it in centimeter itself. 2 into 10 power 22 divided by 10 power 16. I have just converted it into meters. And finally E square, that is the charge of an electron, 1.6 into 10 power minus 19 the whole square into Na2 into 10 power 22. So if I calculate this whole thing, we'll get the value of Wm. So Wm becomes approximately equal to 2.22 into 10 power minus 7 meters, which is approximately 222 nanometers. So this is the answer. So if you have access to this equation directly, you can find out what is the depletion rate at strong inversion. So is it clear?
Yes, ma'am.
Yeah. So I think with that we can wind up today's session. We have covered most of the areas. So in case you have any doubt, please do post your doubt either in the discussion forum or you can mail me at sandra.pnrf@gmail.com. So thank you for joining, Sarla. Like, I'm glad that at least one person joined and we could do the session. Thank you so much, and you can leave.